but it should be hunky-dory. And the final, just so you guys know, so you guys can start prepping for the final is going to cover mostly chapters 1 through 8. The stuff that we're going to cover right now, chapter 9, and the stuff that we cover in 10, 11, and 12, you're likely only to have a couple of questions on the final about it. Because this is the gravy stuff. This is the stuff that we got to get to, get the stuff that we have fun with, and it gets to the gravy stuff. So we've covered most everything that we absolutely have to have, but we've got some other pieces. So for the final, you get to have an 8.5 by 11 piece of paper with anything that you want on it. And at that point, if you want to look at this, let's see if I can get the screen here. If I were drawing up a cheat sheet for the final, this is pretty much what it would look like. Back in the camera. Okay, I'm trying to. Oh, we're having fun now. There we go. Maybe. There we go. Woohoo! Now we get it. Gotta do some focusing, but what's wrong? But everybody's sleeping. Okay, so if I were making a cheat sheet for the exam, this is kind of what it would look like. It's got the angular equations. What's missing on this that you may want to add is some of the stuff from chapter 9, like Bernoulli's equation and the pressure equation, and we'll get to that here in just a little bit. But most of the test is going to be covered with this material right there. And that will be your final. And our final's 8:30 on Monday morning. Your best study guide for the final will be your past tests. So if you haven't gotten your past tests back or want them, they're in my office for those of you here in Tonkawa, and I will have them in my folder with me on Friday over in Enid, so that you guys can get, that you didn't get it handed back. You've got those. And then we have gone over the tests as well. So you've got the videos of those things that have gone over. So you have the videos of all the classes, save a couple that didn't record for whatever reason. And so you've got those for your study guides and your past tests. And your past tests are going to be your best study guide. The other thing that you guys have to deal with is you've got a quiz. That's kind of like a final review or final test prep, or a quiz that says quiz for assessment, or you may have both, because I have both in a couple of them. Those are really good practices for the final, and I will tell you the final won't be as hard as the quizzes. The quizzes are definitely harder problems because I can give you infinite time to work those problems, and I use the quizzes for assessment. So that's what I actually use for assessment. I don't use the final for assessment. For a couple of reasons. The other thing is, many of you are going to ask me, and I'm going to tell you, don't do it. All right? Many of you will ask me, what do I have to get on the final to get such and such? I will tell you that is a mental trap. That is a total mental trap. I have seen it over and over and over again. If you think you need to get 50 points, you are likely to get 45 points. You are likely to get almost there, but not enough. And what happens is, mentally what happens is you go through the test and you go, okay, I got this one, I got this one. You calculate in your head, hey, I've got this, I've got 50 points, and your brain shuts down. And so you don't end up getting the score that you need. because your brain shuts down because you think you've already made the score that you need, and you usually somewhere along the line have messed up just a little bit, and it costs you. So I don't like to give you the score that you have to have. You can play with it and calculate it yourself. One of the things that I have done and will do, because it alleviates a lot of your stress, is put in a 0 for the final, so you know what the absolute worst case would be. And I usually do that like the Friday before, so that you know absolutely this is the worst case. If you walked in and got a total 0 on the final, that would be what your grade would be. And that does usually alleviate a lot of stress for most of you, because most of you, the final's not going to make a heck of a lot of difference. The only people that it really tends to make a difference is if you're right at the borderline. Because most of my stuff is built up with extra credit ahead of time, quizzes, homework, and labs, the stuff that you have absolute control over, is the bulk of your grade, which helps you along the way. So at this point, that's where we're at. Okay, anything else I wanted to, I'll go over the tests a week from Wednesday, because the tests will be done on Friday, so that you'll have that part done. And then next week, like I said, we'll do the thermodynamics. So we get to start with the fun stuff today. So we've been talking about all the way along is that physics is stuff, right? We're dealing with stuff. And that stuff that we've been dealing with is mass or matter. And remember, mass is independent of whether I'm on Earth or I'm on Mars, if I'm on Jupiter, and because that becomes a real key thing with what happened yesterday. I don't know if anybody was paying attention yesterday. The InSight lander landed. It was nice and fun. Some of the physics numbers they gave were great. You know, they went from 12,500 meters per second to nothing on the surface of the Earth, or on the surface of Mars. And we're talking about Mars quakes now instead of earthquakes. That's what that particular InSight is going to be looking at. And so they've sent back the first pictures came in late yesterday as well. So we've been talking about matter and stuff. We know that we have conservation of matter. And most of you have taken at least Chem 1 or are getting almost through Chem 1. And most of you some of you are in Chem 2, so we've been dealing with that. And we've said that the conservation of matter says mass can neither be created nor destroyed. We've talked about conservation of energy. We've talked about conservation of momentum. And momentum can be linear or angular. We've dealt with kinematics. Okay, I can't spell today. Kinematics. So we've done all of these things, and we've all been related. We've looked at F is equal to ma. That was one of the things that we've been dealing with. And we had that torque is equal to moment of inertia times the angular momentum. And that the moment of inertia is related to mass. And so force and moment of inertia are all in what's happening with our mass. So what we're getting ready to do is we're starting to look at matter and some of the parts of matter that we want to be dealing with it. So we're defining stuff. Okay, we're actually going to be defining stuff and looking at matter and how things start behaving. If we've been in chemistry class, here comes the fun part. If we've been in chemistry class, we talk about matter, and the smallest thing of matter that we refer to in chemistry is related to the atom, and we have protons and neutrons in the nucleus, and we're surrounded by electrons. And this atom is the thing that has properties that distinguish. So an atom of hydrogen is going to be different than an atom of helium, which is going to be different than an atom of carbon, which will be different than an atom of lead. And this is all based on the number of protons that are associated with that particular atom. So when we start on the physics world, we start looking at things just a tad bit differently. So when we're dealing with things with certain properties, the smallest thing is what we look at is with an atom. But when we're dealing with physics folks start doing things a little differently. But when we break up an atom, we end up with protons, neutrons, oh gosh, can't spell today, neutrons, and electrons. Now I can take a single proton out there, and if I have a single proton, I have a hydrogen cation, right? Because a single proton is a hydrogen cation. But I've got an electron, and it doesn't matter which atom has it, electrons are all going to be the same. And it turns out that, and if you've taken my chemistry class, I'll tell you that an electron is a fundamental particle of the universe. So we got electrons out there. We haven't been able to break an electron into something else. Turns out about 3-4 years ago, we discovered that the electron was spherical and it doesn't have a pole, okay? It's a negative charge. It sits out there. It has a negative charge, and it is a fundamental particle of the universe that's spherical that carries a negative charge. Well, the same's not true for the proton and the neutron, because we have something that we call atom smashers, and we can break up protons and neutrons, okay? We can smash those into something else. So proton is not a fundamental particle of the universe. Proton can actually be smashed into something else. And so it can be smashed into what we call, and here's the fun part, physicists are weird people. We've got quarks, okay? Quarks, now, here comes the fun part. So quark, the word quark could rhyme with pork, or could rhyme with park. Take your pick. The physics community has argued in letters to the editor when I was in undergraduate school. It went on for a year in the journal, or the Physics Monthly, whatever it is, I can't remember what it's called. Physics Monthly and the letters to the editor, there was a huge argument, tons of letters to the editor as to whether or not the word rhymed with pork or the word rhymes with park. You will hear it both ways, and no consensus was ever occurred. So that's the fun part, all right? That's the total fun part. So there are 6 of them. There's 6 quarks, and they are up and down, charm and strange, top and bottom. Fun names. Okay, now, if I take quarks, and it's usually 3 quarks to a proton or to a neutron. And if we're in chemistry class, right, we know that a proton has a positive charge and a neutron has a neutral charge. Okay? So here comes the fun part. Quarks have partial charge. Now, if I think of an electron comes with just one charge. Electron comes with just a negative charge, and it's one negative charge. Quarks have positive charge or negative charge. Okay? And it works out that they're like 2/3 of a charge. And depending on how I add them up, will give me whether or not I have a positive or a negative. So it's weird stuff when we start adding protons and neutrons, or quarks to get protons and neutrons. Which is also why, because I have fractional charge on my quarks, I have my fractional charge, that one, the neutron is going to be slightly heavier than my proton. And so if you look at the mass, you know that the neutron mass is slightly heavier than the proton. So we've got, so far I've talked to you about 1, 2, 3, 4, 5, 6, and the electron. We have 6, 7 fundamental particles of the universe. Well, that's not everything. If you guys watch Big Bang Theory, you find out that there are a few others. We have 6 leptons. Okay? We have 6 leptons. Now, the electron is one of the leptons. So we have something that looks like this. They could do this, and we do this, and we do this. This is the electron neutrino. This is what they call the muon neutrino. And this is the tau neutrino. And then we have the electron, the muon, and the tau particle. So now we're up to 12 particles because the electron is one of the leptons. And then we have the 4 force carriers. We have the 4 force carriers. And that gives us the photon, the Z boson, the W boson, and a script G. That looks like a Q, but it's a script G for a gluon. And these are the ones that carry forces.
Scientists have weird names.
All right, physicists do weird stuff. Okay? Being a physicist gives me lots of permission. You guys think I'm crazy anyway, so I can be crazy, so it's great. All right? I mean, being a physicist allows you to do a lot of different things. So we end up having 12, 16 particles. All right, I will tell you right here, right now, right up front, this is as far as I go. All right? I am not a high-energy physicist. I am not a particle physicist. And I have a problem with string theory. Okay? Yes, I have taken those classes. Yes, I sit there and I go, I can't get my head around it. That is not me. I play in the Newtonian world. This is where we go. This is where we stop. I play in the Newtonian world. I like Newton's world. It's great. For those of you who know, who've heard me talk in other classes, I am very mentally disturbed by Horton Hears a Who, by the cat's necklace in Men in Black, and the subway locker in Men in Black 2. Okay? Because once you get into the little particle stuff, that's what you're getting into. It's whose clover are we sitting on? All right? And then I have the other fundamental question, which is why physicists were called natural philosophers until about 1918. We were natural philosophers. We weren't scientists. We were natural philosophers. Because if we're an expanding universe, what are we expanding into? Fundamental question. If we're an expanding universe, what are we expanding into? You know, I wonder whose cat's necklace we're hanging off of. So that's just, this is where I stop. Okay? This is where I stop. This is not me. I play in the Newtonian world. So I'm telling you right now. But the Newtonian world does allow us to get into atoms, and atoms are cool. So when we get this part, I start playing with atoms up, all right? So atoms are where we are. So we can combine the quarks into making protons and neutrons, and protons and neutrons, and we got the electron, all that neutrino stuff, all that boson stuff, it's cool. But photons are really great, okay? I will tell you, photons and light are really cool. But I'm a light scatterer, so that, but again, that's Newtonian world. So that helps us out a lot. So we have experience with things atoms up, all right? And size, atoms up. That's what we deal with. That's our realm. And then we just have the other fun stuff. So we combine all of that stuff to give us atoms. And then here comes the other fun part. We lie to you. Scientists lie to you. We start lying to you in kindergarten, right? We start lying to you in kindergarten. We start lying to you all the way around. And then you get to college and we tell you we lied to you. So this is where we start dealing with stuff. And so if you've been in my chemistry class, you've heard this one before, because now we're coming at it from the physics side, all right? I come to chemistry from the physics side. A lot of people come to chemistry from the biology side. I come to it from the physics side. And so we end up with material or stuff, and matter's made up of our atoms, because our atoms are made up with those other particles, and we have other fun things that are going on. Right? So we get to our atoms, and we have protons and neutrons in the nucleus, and we got electrons floating out here. And we do a lot of cool stuff with quantum chemistry to help explain energy states and all those fun things. But fundamentally, what we end up dealing with every day is how this stuff comes together and how this stuff interacts with us, right? So we end up dealing with that out there. And matter has various physical properties, which is why we like to do with chemistry. It has mass. We can talk about conductivity. We can talk about resistivity. We have size. We now have volume. We can talk about reactivity. And that's where all the chemistry stuff comes in, all the fun stuff and the chemistry stuff, right? This we're dealing with the properties. But one of the properties that we talk about is their normal state. Okay, their normal state. So sitting in this room, we are looking at two fundamental normal states. Okay, two fundamental normal states we've got that we encounter that are here, and they are, we know our states of matter. So this is where we start lying to you. In chemistry class, I'm going to tell you there are 3 states of matter. Okay? In chemistry class, we tell you there are 3. Right? The 3 we tell you in chemistry class are gas, liquid, solid. Okay? Physics class, I'm going to tell you there are 4. We're going to add one. And actually, in the room that you're sitting in, we actually have the 4th one. Because we have fluorescent lights up here. So we got the 4th one. The 4th one is plasma. But I'm still going to tell you we're lying to you. So, if you're in my chemistry class, and I have a couple of you in this room that are in my chemistry class and in my physics class, if I give you the question in chemistry class and ask you how many states of matter there are, you're going to tell me 3. But if I give you the test in my physics class and ask you how many states of matter there are, I'm going to tell you 4 is going to be the right answer. But neither of those answers is right, because we lie to you. All right? Neither of those answers are right because we lie to you. Okay? So, plasma, we'll give you the formal definitions. All right? The formal definitions. Plasma is an ionized state with neutral charge but it has electromagnetic properties. Think of what's going on inside of a neon tube, okay? I get that ball of gas has it has a lot of interesting properties. I can actually form plasma balls. It actually does weird things, but it's a charged ionized gas that has certain different properties. So those are plasmas. Solid, by definition, has a defined shape and can stand alone. Okay? Solid has a defined shape and can stand alone. So we know solids. The chair you're sitting on is a solid. It's a good thing. Because if it weren't, we'd have problems. Okay? Table, the desks, all those things are solids. Nice, fun solids. That leaves us with gases and liquids. One of the definitions of gases and liquids is that it takes the shape of their container. But that's not enough of a definition, okay? It's not enough of a definition to say that it takes the shape of their container. The interesting thing is, what we're about to start talking about are fluids, and gases and liquids are both fluids, okay? But there's different properties whether or not I have a liquid than if I have a gas, right? One thing about a liquid is it's considered to be incompressible, all right? It's why I can have hydraulics. If I have a liquid or hydraulic fluid, if I put it in a piston and I try to press that piston down, I'm not going to go too far, okay? I'm not going to go too far. Conversely, if I have a gas and I put it into a piston, like a bicycle pump, I can compress the gas. So a liquid is going to be incompressible and will allow us to do certain things, whereas a gas is compressible and it's going to have slightly different behavior. But there are going to be similar properties between a gas and a liquid for certain aspects that allow me to call it a fluid. And that's where Chapter 9 is really getting us to, is looking at some of those different properties associated with the states of matter. So then comes the question, what's the difference between a gas and a liquid? They both take the shape of their container, right? And there is actually a paper, it finally got published, that a cat is a fluid, okay? Because if you actually take the definition of a cat, or definition of a fluid, and you put a cat into a sink, what's the cat going to do? Not filled with water. It's going to take the shape of its container. So a cat can act like a fluid, okay? Physicists sometimes have fun with certain papers. I have witnessed it over Thanksgiving. My son's cat actually went into a bag and likes to take the shape of the container it likes to crawl into. So it will take the shape of its container. It will show fluid behavior. It also shows solid behavior as well, because it's pretty well solid. It can stand on its own. So it's kind of an interesting, fun piece. If you ever want fun reading, read the Journal of Irreproducible Results. It's always a fun thing. So we talk about fluids. So the difference between a gas and a liquid, fundamentally, is if I have a jar, I'm going to draw two jars. And I look at my jars. This one has a gas in it. That one has a liquid in it. So my distinction between my gas and my liquid is I have a defined interface. This part of the jar is still filled with gas. This part of the jar is filled with liquid, but there's a defined interface between the two. So if I have a water droplet, I have a defined interface. If I have an oil droplet, I have a defined interface. And that's what's going to give me the difference between my gas and my liquid. So those are our major classifications for states of matter. Now I'm going to complicate it because I can't lie to you. if you were to ask me how many states of matter there are, I'm going to tell you it's under debate. I've seen, recently I've seen 7, I've seen 9, all right? 7 or 9. There's a big debate, and so we're going to talk about where the debates are. So this is where the debates come into play. I'm going to ask the question. Most of us have played with silly putty.
Yeah.
Is that a solid or a liquid?
It's an amorphous solid.
Is it a solid or a liquid?
It can act as both, depending on how you mess with it.
That's the question. Is it silly putty? It takes the shape of its container over time, doesn't it? So it's a fluid.
But it's also can be hard as a rock sometimes.
Depending on what I'm doing, it can act as a solid. So silly putty has a problem. So silly putty is a problem. So that's a weird one. Here's another one.
Well,
Is that a solid or a liquid?
it's solid. But
No. Takes the shape of its container. It actually can flow. It jiggles.
But it's
Okay? So there's 2 substances that we're having trouble classifying.
but it has a defined shape.
It can have a defined shape. You leave it defined now, unless you do jigglers, you know, if I'm making my Jell-O jigglers, it'll actually hold its shape. But if I do Jell-O molds on the summertime, they have a tendency to do other weird things. Okay, so that's another one. I'll give you another one.
That's solid.
Nope. Actually, lead glass will flow. Time scales are like 100 years. Time scales are long.
It's a very viscous fluid.
It's a very viscous fluid. Yeah, time scales on lead glass, 100 years, or on the order of 100 years. It will flow. Okay, glass will flow. So the distinction between a solid and a liquid is a little weird. Okay, so all of these, the distinction between a solid and a liquid is weird. So the cleaner definition of a solid is that if I have like sodium chloride, right? So here's my chlorine atom, here's my sodium atom, and I put these in together and I'm making a salt crystal. I'm making a salt crystal. It has a defined structure. And so you were right when we talk about an amorphous solid versus a crystalline solid. And that's where we end up talking about whether this is crystalline or not, where I'm going to get a defined structure. My defined structure can be cubic. And this is where that fun part of the Natural History Museum is, because you can go in and you can find cubes. Then you can find quartz crystals that have like that 6-sided shape associated with them, and you get nice crystals that look like that. You get diamond has a structure that's a little different. You get a variety of different crystalline structures. And we usually talk about, in terms of chemistry, we talk about allotropes. And allotropes are different structures associated with the same substance. Carbon is great to talk about allotropes because graphite is actually a 2-dimensional solid. Okay, it's a 2D solid, whereas diamond is a 3D solid. And even though those are both solids and they're both made of actual just carbon, they have very different properties associated with how that crystalline structure comes in. Graphite becomes an incredibly good lubricant. Diamond is the hardest stuff we know. So we get a variety of different pieces, and then you can start listing the other gazillion different crystalline structures of carbon. Buckyballs, carbon whiskers, carbon nanotubes, carbon fibers. I mean, there's a whole host of different things for carbon, but all of them are very crystalline structures, okay? All of them are very crystalline structures. Glass, actually, we talk about glass, depending on our glass that we have. Like I said, lead glass actually does have flow properties, but we're on time scales that are centuries long, but it's an amorphous solid. Let me see if I can spell it right. Oh, I did it wrong. Amorphous solid. That if I'm looking at its structure through X-ray crystallography, I don't have a defined structure. It's more of a network, per se. And that's when silly putty is in its solid form, it's more of an amorphous solid. Gotta get there. So glasses have some different properties than another amorphous solid. So glass is an amorphous solid, and that gets us into something that we call gels. Gels are also amorphous solids. There's not a defined structure. There's a network that's holding it together, and they have different behaviors. So you do get two different types of amorphous solids, but gels and glasses are usually separated when we talk about them in terms of material properties, because their material properties are very different when you have gels. And so silly putty is more of a gel. Silly putty is also non-Newtonian, and we'll talk about Newtonian fluids and non-Newtonian fluids, because non-Newtonian fluids are really cool. Non-Newtonian fluids are fun. And silly putty is a non-Newtonian fluid. And so we'll actually get into that a little bit. So we got gels, we got glasses, but now that gets us, so for counting, now I'm up to 4 states of matter plus 2, I'm up to 6. And I told you there's like 7 to 9, okay, depending on who's arguing. And that comes into the really weird world of physics, that everything that we've talked about there is that we can encounter in our everyday worlds, in our everyday lives. What gets now fun things are what they call condensates. And they're like Bose condensates, Bose-Einstein condensates. There's a lot of weird things that they talk about, but as I get close to 0 degrees Kelvin, or 0 Kelvin, because we don't use the degree sign for Kelvin, if I get close to 0 Kelvin and I got a bunch of atoms, not only do they form a different structure down here as they stop moving, I can't distinguish one from the other. They're actually also going to be in these same electronic states. So they have different behavior than, say, a normal material. And so you get these weird things that the physicists are out there saying, okay, you know, if we're down at 0 degrees Kelvin or 0 Kelvin, what are we doing? And there's a debate, do I have more than one condensate? Do I have a range of condensates? And that's why I can't tell you exactly how many states of matter there are. But for our purposes, if I ask you the question on the physics test, it's 4. Because we lie to you. Okay? We totally lie to you. If I ask you on the chemistry test, it's 3. Because we don't count plasmas. So we talk about the fun part. So, all right. So now you know. Now we play with that kind of stuff. Okay. So we have more fun. So we've talked about that. The atom becomes our thing that has specific properties. So we can look at our periodic table and we know that carbon is going to have 6 protons. If it's neutral, it'll have 6 electrons. And its normal, what we refer to as its molecular weight or its atomic mass unit, atomic mass unit. That's going to tell us what the average, if I were to pick up a carbon atom, just pluck out one carbon atom, what is it going to weigh? That's, how much mass is there. And carbon-12 is going to have, so if I have a carbon atom, I'm going to have 6 protons. There's my 6 protons. And I'm going to have 6 neutrons. And I'll have 6 electrons out here in their correct orbital states. Okay? So if I got my carbon atom, I got my 6 electrons, my 6 protons, and my 6 neutrons. But if I have carbon-16, because we have things called isotopes, that varies in the number of neutrons. I have more neutrons in different isotopes. So if I have carbon-16, I'm going to end up having my protons, and I'm going to throw in some more neutrons to have fun. We end up with those fun things. If I have carbon-14, I'm going to have 8 neutrons and have fun things. So we end up with little differences, but they're going to have similar properties. It doesn't matter whether carbon-14 or carbon-16, it's going to have similar properties. They're going to behave similarly. So we end up with that. Fun fact, anybody catch the news over Thanksgiving break?
Oh, about they changed the weight of the kilogram?
It changed the weight of the kilogram. Changed the weight of the kilogram. So the question is, does that make a difference?
I want to say yes, but that feels like a trick question.
Actually, it is yes. It is yes. It does make a difference. Because by changing the weight of the kilogram, or changing the basis for the kilogram, it affects a lot of stuff. The big thing that it affects, and there are a bunch of us that went, oh no, it's going to change things. One of the things that changes is, if we look at the definition of a mole, remember the definition of a mole relates back to the number of carbon atoms in a gram. So if I've changed the definition of the kilogram, I've changed the definition of the gram. And if I've changed the definition of the gram, I've changed the number of atoms, of carbon-12 atoms in a gram. So I've changed the number, I've changed Avogadro's number. So I have changed Avogadro's number. So if I've changed Avogadro's number, guess what? All the atomic masses on the periodic table change.
Everything. Why did it change it?
Because kilogram was losing weight.
Why was it losing weight?
Well, we'll talk about that in a second. Kilogram was losing weight.
On a diet?
Well, sorta. Okay? We'll talk about that in just a second. Now the question is, does it matter?
Yes. No.
It depends on what scale you're in. Now, will our periodic tables that are measured to 3 significant figures past the decimal point change? Nope. But if I am measuring parts per trillion, okay, if I am looking at parts per trillion, I may have a problem. And so for analytical chemists, there was a little bit of consternation as to how big the change was going to be. Because if I'm in the parts per trillion, it's potentially significant. But if I'm in the parts per million, not so much. All right, and that's where the fun part came in. The whole debate. They actually announced it about 4 years ago that we were going to change. And so several of us kind of had hyperventilated it a little bit because I was working in analytical chemistry. I work in environmental chemistry. And so there are things that we do measure on a part per trillion level. And then we got to thinking about it and we go, okay, it's not affecting us because of where the change is not in the order of magnitude that we're worried about. Parts per trillion, potentially. Parts per billion, not so much. All right, so now why did the kilogram lose weight? So back in Switzerland, we have an object that was 1 kilogram. It's sitting out there 1 kilogram. So let's instead of a solid, because we tend to think solids aren't going to change, all right? We tend to think solids aren't going to change. But I'm going to make an argument that solids change. So let's look at a cup of water, all right? If I set a cup of water on this counter right here, if I set my cup of water right here, and we watch it over the next week, let's say I put in a half a cup of water out there, just to give us something to, 4 fluid ounces. If I come back here next week, do I have 4 fluid ounces in my water glass? No. Because it's evaporated, right? It's actually evaporated. It changed state from water to a gas, because we know what happens, right? I've got my little water molecules are sitting here floating around. They're moving around. And every now and then, one is going to pop up and go above that surface. Well, over the course of 100 years, because if I'm sitting up on the top of the mountain, and even though it never gets above freezing, and we've all experienced this, we've even experienced this here in Oklahoma, I can have a pile of snow out here, and even though it never gets above freezing, the snow disappears. And it's not just due to the wind. And it's not due to the sun. The snow disappears because this sublimates. And we see it with water all the time. That ice will essentially go from a solid to a gas. We experience it a lot around, a lot of us deal with it when I deal with dry ice. We see that really quickly with dry ice. Dry ice does not go into its liquid state when I take it out of the freezer. It goes straight to a gas. So it sublimates. So even though my kilogram was made out of, I don't know if it was made out of pure gold or if it was made out of a pure substance, it could have been bronze, I don't exactly remember what, but our basic standard kilogram that was tied to a physical object, and how they discovered it is they compared, there were like 12 of them, and the National Institute of Standards had one, and they would compare the masses of the standard masses, and they would find out that, guess what? It was losing weight. It was losing weight because it was sublimating. Over time, the vibrations of my particular object had a few atoms, and over the course of 100 years, on that time scale, guess what happened? A 1 kilogram was no longer 1 kilogram. It was more like 999.5 grams instead of 1,000 grams. So it got significant enough that, and it was the last standard that was actually based on a physical object. We got rid of the meter a while ago. The meter, there used to be an actual standard meter, and now the meter was defined as the distance that the speed of light would cover in a certain time frame. That light would cover in a vacuum in a time frame. So we actually deal with a standard that's based on a fundamental constant of the universe, and that's what we did. We changed it back to a fundamental constant in the universe, and the kilogram is now based off of Planck's constant rather than a physical object. So yes, all right. So we end up having a change, and so our atomic mass units will change, but it's still it's going to end up being the number of grams per mole, where the mole is defined, associated as the number of carbon atoms in a gram, and 1 mole. And for most of us, we don't even see the difference in the new mole. It's 6.022 times 10 to the 23rd number of items, whether that's carbon atoms, whether that's iron atoms, whether that's bolts, whether that's widgets, whether that's grains of sand, eggs, planets, galaxies in the universe, Doesn't matter. It's just a way of counting things, and it's just a way of grouping a very large amount of things that we end up with. So that gets us to a property that we've all played with and all have dealt with, and that is density. Density, we use the Greek symbol rho. It's defined as mass per unit volume. I can also have something that's called a weight density. Usually we use a W on the bottom to give us that distinction between the weight density, and the weight density is the weight per unit volume, because we know that weight is a force, and that's equal to the mass times gravity. Because we've been dealing with that. Standard units are kilograms, meters cubed. Most of the time we use grams per meter cubed. We can calculate densities. So if I have a box, okay, if I have a box, and this is 1 meter by 0.5 meters by 2 meters, everything's in meters. We know it's the length times the width times the height will give us the volume. And so I can do 1 times 0.5 times 2 is going to give us, oh, I didn't bring my calculator. Anybody got a calculator? Punch that in.
It's 1.
Thank you. I probably could have figured that one out by thinking about it. That's meters cubed. And if this has a mass of 1.5 kilograms, we know that the density is going to be 1.5 kilograms divided by 1. And this is going to give me 1.5 kilograms meters cubed. And we don't give it a special unit, which is really nice. This is related to specific gravity. Okay, specific gravity is the ratio of density of the material to the density of water. And the density of water is 1.0 times 10 to the third kilograms meters cubed, or 1 gram per centimeter cubed, or 1 gram per cc. So we can MacGyver a lot of different things, because most of us have a standard with us or readily available, and that standard is water. And we do a lot of things associated with the standard of water. So density, and we compare densities all the time. We compare densities all the time in terms of how it's compared to water. You know, oil has a density less than water, so it's going to float. Lead has a density more than water, so it's going to sink. Some things get suspended, so we get a variety of different parts, but we do specific gravity. Common volume calculations, so guys should remember this from way back when. It's also in the appendix of your book. We know that if I have a rectangular shape, it's going to be length times width times height. If I have a sphere, it's 4/3 pi r cubed. If I have a cylinder, it's going to be pi r squared, which is the area on the top, times the height. So we get pi r squared times h, which is going to give me area times the height. And you can do cones, there's lots of different charts that are a variety of different pieces. So we can do a variety of different things. Okay, I've got time for one more thing. So now the question becomes, why, if I have an object that has a mass like this, we know its weight is going to be the same, but we know that if I turn it on its end, those two situations are different. We fundamentally know that. Because most of us have experienced the following. If I take a woman's shoe, and if it's a flat shoe versus a shoe that looks like this, and we have those things step on our foot, what's going to happen? And which one hurts more? This one. Right? The weight of the person's the same.
Smaller area.
There's a smaller area.
Meaning more force being applied on that smaller area.
Well, it's not, it's related to the force. That's where we define this. We define something called pressure, and that's force per unit area.
So that's a smaller area, meaning the pressure is a lot larger.
Right. Smaller area means the pressure is a lot larger. And my favorite example is this. I use this example quite a bit. I have a 900-pound.
So what you're saying is that a tall, skinny object would be more painful to get stepped on with than a wide object.
So I have a 900-pound quarter horse, and we'll take a reasonably sized woman, 135 pounds. We're going to use pressure. We'll do it in units that most of us are familiar with, and we're going to do it in pounds per square inch or in PSI, because most of us are very familiar with this kind of a number. If we put all the weight of my 900-pound quarter horse, except he's more like 1,000 pounds right now, and we put all the weight on one foot, my quarter horse, he has tiny feet. He's a dainty quarter horse. He has size 0 shoes. He's got small dainty feet. His dainty feet has about 16 square inches. It's the size of one of his feet. If I give it a reasonable woman's heel, and we're going to put all the weight on a reasonable woman's heel of 1 square inch, okay, that is a reasonable woman's heel. I've seen pointier ones out there. We have the difference there, the pressure that's applied by my 900-pound quarter horse. Somebody plug that one in, because I know what the other one's going to be. 56.25 pounds per square inch versus my 135-pound woman over 1 square inch, 135 PSI. I would tell you I would have my very large horse with his very large footy step on my foot over having even a very tiny woman stepping on one of those spiked heels on my foot. There's a big difference. So pressure is one of those big difference things. One last thing before we call it a day, that pressure, if I'm in SI units, are Newton meters squared, which is defined as a Pascal, which is a PA. And that is a derived unit. All right. We're going to call it a day. You've got your test out there.
That killed